여러분 안녕하세요. 이 시간 저는 진행을 맡은 미래문명원의 부원장 신은희 교수입니다. 반갑습니다. 오늘 이 뜻깊은 자리에는 총장님을 비롯하여 해외 석학, 국제기구 대표자, 교직원, 학생, 동문 여러분들께서 참석해 주셨습니다. 경희대학교는 매년 UN 세계평화의 날을 기념하여 기념식, 국제학술회의, 학생활동 등을 전개해 오고 있습니다. 올해는 전환문명시대 한반도, 가치와 철학이라는 대주제로 오늘부터 20일까지 다양한 피스바 학술 행사와 실천 운동이 캠퍼스 내외에서 진행될 예정입니다. 오늘은 그 첫 번째 날인데요. 특별히 오늘 학술회의는 기후변화센터와 인류사회재건연구원과 함께 공동 주관으로 진행하고 있습니다. 내빈 소개는 잠시 후 패널 토론 때 소개해 드리도록 하겠습니다. 오늘 국제학술회의의 주제는 사라지는 빙하, 기후변화와 지구평화입니다. 지난 여름 지구촌 전체가 폭염과 이상기후로 고통을 경험했는데요. 이러한 현상이 앞으로도 지속될 것이라는 다소 암울한 전망이 나오고 있습니다. 이 분야의 최고의 석학이신 우리 피터 와담스 교수님과 함께 기후변화와 평화, 또 미래 사회에 관한 성찰의 시간을 다 함께 가져보았으면 좋겠습니다. 와담스 교수님께서는 캠브리지 대학교의 명예교수이시고요. Farewell to Ice의 저자이시기도 합니다. 이제 피터 와담스 교수님을 앞으로 모시고자 합니다. 여러분 큰 박수로 와담스 교수님을 환영해 주시기 바랍니다.
Thank you very much, and I'm very deeply honoured to be invited to this wonderful place. It's my first time in Korea, and I really admire your university and the wonderful things it's doing. Also, I want to thank the university for arranging for the translation of my book, and that's another great honour because. To make it available to Korean readers is something which I think is hopefully very worthwhile, and something which the university did in record time. What I'm going to talk about is, I call it a farewell to ice because for two reasons. One is that we are losing the world's ice at a very rapid rate, and especially the ice in the Arctic Ocean, and that's what I'm going to be talking mostly about. But we're also losing ice everywhere else as well, in Greenland and Antarctica. Eventually, we're going to become an ice-free planet, as we were maybe 50 million years ago. So it's a farewell to ice as an element in our planetary system. But it's also a personal farewell because when I started out doing ice research about 50 years ago, there was plenty of ice around to study, but now there's less and less. So this is just to advertise my book, which until now was only available in English or Italian, if you prefer that. So I'll start by looking at what's happened to ice in the world and how much of it there is. And this is a misleading map because it's divided into 5 periods of history with gaps in between and different scales, so it's not a good scientific map. But if we look at the first one, where it's all the yellow and the red, this is data from way back 100 to 500 million years ago. We don't have very much data about the Earth's climate at that time. There's some people say that there were periods in several hundred million years ago when the Earth was a snowball. It got suddenly very, very cold. But most of the data we have shows that the Earth was warmer than it is now. 0 here is present-day climate. So the average temperature of the Earth was about sort of 6 to 8, 10 degrees warmer than now. Then in the period between 60 and 10 million years ago, the Earth started to cool off, and again, we don't quite know why, but it gradually cooled until it reached the point about 1 million years ago, that's the end of the third page here, when it could form, it was possible to form ice sheets. And the way that happens is that if you have a high mountain and the snow and waterfalls of snow in winter, and that snow doesn't melt in the summer, then the next winter some more snow will fall on top and compress the layer beneath, and eventually that builds up to an ice sheet, a glacier or an ice sheet, depending on whether it's a mountain or a flat plain. So you can build up ice sheets if the temperature is cool enough. And it reached that point in about 1 million years ago, and we started to have, instead of having a continuous ice sheet, we had this oscillating system, which is shown in the fourth page. And these are the ice ages, and they're caused by the fact that the amount of radiation acting on the planet slightly changes over a period of about 100,000 years. It's not due to the Earth moving closer to the Sun. It's because there's a change in a number of different angles related to the Earth's orbit. The angle of the Earth's rotation to the Earth's orbit changes gradually. It's called the Chandler Wobble. It's like a spinning top that's running down slightly. That changes, and so the angle of the tropics changes, the latitude of the tropics. And then on top of that, we have the ellipticity of the Earth's orbit changes as well. It moves, becomes flatter or more elliptical. And the time of year when the Earth is closest to the Sun also changes. So these three cycles gradually affect how much radiation reaches the northern hemisphere compared to the southern. And that's important because most of the land is in the northern hemisphere, and that absorbs radiation in a different way from ocean in the southern hemisphere. So with these three cycles, which are called Milankovitch cycles, after Milankovitch, who was a Serbian scientist. There's a movement in Scotland that the person who really thought of this was a person called James Kroll, who was a kind of worked in Edinburgh. But anyway, Milankovitch is the one who gets the credit, and this gives you a cycles which give you alternating cold and warm periods, each lasting about 100,000 years. And that's giving us these ice ages where it's the average temperature of the Earth is just enough that in a cold period we grow ice sheets, in a warm period the ice sheets melt. So that's those cycles there. And then the very last bit of this curve shows what's happened since the end of the last ice age. About 20,000 years ago we started to recover, and 10,000 years ago we were up to a warm period, which we're still in, called an interglacial. Now, if I had a pointer. Okay, well, if we look at the top picture here, we see the temperatures over the average global temperatures over the last 400,000 years, which we can get from data mainly from ice cores, where you drill down through ice sheets and you can get at the global temperatures, the temperature at which the ice sheets, the snow fell. And we find there's a kind of a sawtooth pattern where the ice sheets can form very slowly, because you can only add one layer a year. But if the climate warms up, they can melt very quickly, because many years of ice sheet can melt in 1 year. So we have a sawtooth of slow growth, rapid decay. And that sawtooth pattern is repeated through each glacial cycle. And we are now in the warm period, which thank you. Okay. I can... never mind, I can go and stand by it. Well, the bottom curve shows the same period, but looking at carbon dioxide concentration. And now it's possible to work out what carbon dioxide concentration in the atmosphere was in the very distant past, because when the snow falls to form an ice sheet, it gets compressed. Little air bubbles get compressed until you have tiny high-pressure air bubbles inside the ice sheet. And if you can manage to get at those, you can find what the carbon dioxide concentration was. So we can see that the carbon dioxide concentration varied in the same way as the temperature. And when the temperature's warm, you have a lot of carbon dioxide in the atmosphere. When it's cold, you have a lower level. But it oscillates between two natural levels, which is surprising that they should be the same, but they are from one glaciation to the next. And the natural level during an ice age is about 180 parts per million, and in the warm interglacial periods, it's 270 parts per million. So it's not. Okay, well, it's working now. So if we go from that to the most recent era, we have data still from drilling ice cores, but we also have data from other sources like tree rings, corals, and even in the last couple of hundred years, thermometers. And this bottom graph here shows the estimate of how the northern hemisphere has changed in temperature since the year 1000. And it shows initially a very slow cooling. And this is what you'd expect, because we are, in principle, heading slowly towards the next ice age. But a lot of scientists now think we won't reach it because we've added too much heating with carbon dioxide. But we were heading very slowly downwards, so that it was getting cooler. For instance, in the year 1000, the Vikings were able to settle in Greenland, and then it got too cold for that, and they became extinct in Greenland. But around about 1850, it got to be the coldest yet, and then suddenly the temperature bounded upwards, and we can see how fast it went up after 1850. The upper graph shows an expansion of that last 150 years, and we can see that the increase actually happened in two phases, one up until about 1930, and then another one for about 1960 up to now. Now, the lower graph shows this was a curve which climate change deniers made huge efforts to undermine and said this must be wrong. But in fact, it was thoroughly tested and found to be valid. And it makes it clear that the change from the year 1000 is a natural change. The variability and the rate of change are within normal natural limits. But what happened from 1850 onwards couldn't be natural. It's much too rapid. And this is clearly the result of the Industrial Revolution and us putting carbon dioxide into the atmosphere by inventing steam engines and to power factories. And I'm not sure. Oh, okay. At the same time as the temperature shot up after 1850, so did some of the the climatically active gases in the atmosphere. And the two chief gases that do all the damage are carbon dioxide, that's in the upper curve, and methane, which is the middle curve, and nitrous oxide is a lesser agent at the bottom. But we can see that carbon dioxide was doing exactly what it had done in those ice cores. That is, it came up to 270 at the end of the Ice Age. So from 10,000 years ago until 150 years ago, it was at 270 parts per million, then suddenly shot up. And that curve's a bit out of date. It's now 410. So we've added 50% to the carbon dioxide level of the atmosphere. We've added even more to the methane content, which is now 2.5 times as great as it was at the beginning of the Industrial Revolution. When it was 700, it's now 1,800 parts per billion. So there's a coincidence between adding a lot of greenhouse gases to the atmosphere and the temperature going up. Okay, well, the person who was actually able to make sense of that was Vant Arrhenius, a Swedish scientist. And when we sort of beat our breasts about the evil that we're doing to the planet, there was a period of about 50 years when we didn't need to beat our breasts because we didn't know what we were doing to the planet. That is, we started the Industrial Revolution. We had no idea that carbon dioxide was a greenhouse gas. We didn't know what it was doing to the climate, and there wasn't any way of representing that theoretically. And it was only when the gas laws were discovered, the Stefan Boltzmann law, that in the late 19th century, that it was possible to assess the actual greenhouse effect magnitude, which is, as we know, the fact that we're balancing the incoming radiation from the sun, the shortwave radiation, against the outward longer wave radiation from the Earth, and they balance with the addition of the fact that some of the outgoing radiation is absorbed by carbon dioxide in the atmosphere and other gases as well. And that means that in order to achieve a balance between incoming and outgoing, the planet has to warm up so that it can emit more long-wave radiation. So adding carbon dioxide or adding methane is guaranteed to make the planet warm up. So that's sort of high school physics, but there's still climate change deniers would deny high school physics, which is like denying that the Earth is round or goes around the sun. So Arrhenius came up with the first model in 1896, which showed how much warming would happen with a given amount of CO2. Now, it didn't create much of impact. In fact, it's 122 years later, it still doesn't create much impact because he thought that all that extra carbon dioxide would be absorbed by the ocean. And there was no evidence for that, but he thought that would happen, and therefore we didn't have to worry. So we had an excuse for not doing anything about climate change before 1896 because there was no theoretical basis for understanding what was going on. But now there is, or now for the last 122 years. But when we look at the warming, so we can go back now to looking at the warming curve, and we look at this warming curve for the last 150 years, and instead of looking at the whole planet, if we now look at the Arctic only, these are weather stations between 60 and 90 degrees north, we find that we have the same effect. That is, there was a warming, a kind of hold back for 20 or 30 years, and then another warming. So it's the same pattern of warming that we had on the worldwide map, but if I can get back to that. Okay, right. If we look at the top graph there, it shows this warming after the Industrial Revolution with a little holdback, which we think is due to emission of a lot of soot, of burning brown coal during the 1940s, 1950s. And then that produced a masking effect, and then it warms up again. But that's, and we look at how much warming there's been all told since 1850, it's about 0.8 of a degree. Now, if we now move forward, if we now try to move forward, okay, we find the same shape for the Arctic regions, but the magnitude's much greater. Instead of 0.8 of a degree since 1850, we're now looking at more like 2 to 3 degrees. So the whole thing is amplified and magnified, and the Arctic is following the same pattern as the rest of the world, but with a much greater amplitude. This Arctic amplification means that the Arctic, sorry about this thing is not working properly, so this amplification is found to be greatest at highest latitudes, and if we look at the global average of warming rates, we find that the Arctic is several times, up to about 4 times as great a speed of warming as lower latitudes, including the Antarctic. It looks like you're never going to get free of that particular graph. Okay. Well, this big increase in warming rate in the Arctic means that the predictions of global climate models give you a much bigger amount of warming in the Arctic. And this is the prediction on the right. This is a set of predictions for the end of the century. And this is the sort of older IPCC predictions with business as usual and reducing our carbon emissions and letting rip. And the mid one is the business as usual. And we can see that while by the end of the century, most of the planet gets about 4 degrees of warming, the high latitudes in the Arctic get more like 7 or 8 degrees. It's not 4 anymore, but it's still 2. And that amount of warming is going to be sufficient to really get rid of most of the ice that remains in the Arctic. Next slide, please. So we can expect that this increased Arctic warming would have an effect on the sea ice, because it's a very thin covering over the ocean. And indeed, when you start to look at data from the extent of sea ice at different seasons of the year, we find that a reduction was detectable by about 1950 on the summer months, that's July to September, and there's been a kind of linear decay of area in summer ever since. These other curves are for winter, spring and autumn, when you don't get as much of a retreat, because we're dealing with ice which is right up against the coastlines of the Arctic, and whereas in summer it's shrinking back from the coast. And next slide, please. And that first became noticeable, that was a few percent a year, but first became really noticeable in 2005, that's the little picture on the right, where for the first time there was a complete slot of open water all round the edge of the Arctic, north of Siberia, north of Alaska, and it would enable you, if you wanted to sail around the Northern Sea route or through the Northwest Passage. And the pink line there is what used to be the seasonal average for the summer, for August, September. And you can see that the seasonal average for sea ice in summer used to be more or less right up against the coast of the Arctic. So the Arctic Ocean itself remained ice-covered year-round with only a narrow gap. But the retreat was in the subarctic seas, the Bering Sea and the Atlantic and the Baffin Bay. So that was 2005. So you could see something was happening. But in 2007, something more violent happened, that a huge chunk disappeared out of the seas north of Siberia and Alaska. And we can see the difference between that ice extent and what the seasonal ice extent used to be. It's about half the Arctic Ocean has suddenly become an open sea. Next slide, please. And 2012 took it further. The yellow line is 2007 and the white is 2012. So that's the record low so far, although it's been hovering round about that figure since then. Next slide, please. And this was the ice extent as measured, that's the red, and we can see that climate models were shamefully slow in picking up on whatever processes were causing this, because the black line here is the median value for all the climate models used by IPCC, and they were predicting there'll be plenty of ice left in the summer right until 2100, and here we are down to nearly that level in 2012. So there's something needs doing to the way that sea ice is modelled. Next slide, please. So all of these measurements and observations from satellites involved only extent. There was no way of measuring thickness from satellites, and there still isn't really. So to measure thickness, you have to go underneath the ice. And the first time that was done was in 1958 with the Nautilus, a submarine with an echo sounder looking upwards at the bottom of the ice. So the British started doing this in 1976, and since then I've been on all of the British submarine voyages to the Arctic. And each time they do invite scientists to go along and measure ice thickness and do other measurements as well. So this was our 1976 voyage, where kind of young looking people, one of whom is me, are standing around at the North Pole. Next slide, please. And this is what we found, and this was the surprising thing that was found in 1958 by the Nautilus, that instead of the ice being fairly flat on the underside, reflecting what you see on the top surface, you've got extremely deep ridges, called pressure ridges, that can extend down to 50 meters or more and contain actually more of the mass of the Arctic Ocean ice than the undeformed ice. That's the ice that's grown to a natural thickness by freezing of seawater. So you see some natural ice here of different ages, and then some pressure ridges sticking down. And pressure ridges are caused by convergent wind stress crushing the ice and pushing down, creating a kind of underwater slag heap of ice blocks. Next slide, please. And this is the same thing upside down, so this is what goes into the computer. Next slide. Okay, so if you're collecting this data, this is just a little aside that it's not all that comfortable to collect data from a submarine. If you're a civilian, you get to sleep in a torpedo storage rack, and you don't have a cabin. And also, the submarines we were using were quite old and had a tendency to leak a certain amount of radioactivity. So they advised us as to which part of this torpedo stowage compartment we should sleep in and which ones we should avoid. So this is some of the discomforts you encounter in a submarine. Next slide. Okay, you can also do work from a submarine studying the ice forces on structures, and so to do that you get off the submarine and set out your instruments, and then it submerges and comes up through the ice. Next slide. And here, this is just a couple of scenic views of what the Arctic looks like when you're standing on the ice, hoping that this submarine will actually surface. Next slide. And there it is. And then you get back in. Next slide, please. Well, the data that you get out from this submarine is really useful because it gives you a complete distribution of thickness of the ice. Every 50 to 100 kilometers, you can add together all the data that you've collected with your upward sonar, and you get these kind of representations of distribution of ice thickness. The peak is the preferred age of the ice, the natural thickness it reaches by growing just by freezing of seawater, and then the long tail on the right of each curve is the ice that's contained in pressure ridges. Next slide, please. And we can already found that, for instance, old ice, that's, for instance, ice north of Greenland, which is the oldest ice in the Arctic, which, as you probably saw in the papers a couple of weeks ago, has recently broken out and disappeared. But that old ice contains a lot more ridges than the newer ice, which is listed here as both at sea. The more ridges and thicker ridges. So that's what the old ice was, really rugged kind of material, but younger ice is not. Next slide. And the ice obeys very, very rigorous laws of statistical laws of how much ice there is of different thicknesses. It follows a negative exponential distribution. Next slide. So I'll leave that behind and go on with what the results mean. This is that you can do surveys over a grid with the submarine. Next slide. And then the very last voyage we did, which was over 10 years ago, mainly because there was an accident on that voyage and a couple of sailors were killed, and there was an explosion. So the Navy stopped sending submarines to the Arctic. But that was the best, apart from the accident, that was the best voyage for data gathering because we fitted a multi-beam sonar on the submarine and was able to get three-dimensional images of the bottom of the ice. Next slide, please. And this shows, this is one image which shows a pressure ridge in 3 dimensions. So instead of just having this thing sticking down, you can see that it is actually a ridge, and you can see its structure, how long it is, and what its slope is. Next slide. Anyway, the data now covers nearly the whole Arctic. The black box here is called the Gore box. That was when Vice President Gore was chairman of a committee that was looking at data gathering from the Arctic. He said that the Americans should produce all the data that their submarines generate within this region that's definitely international waters, the Gore box. So the Royal Navy sort of ignored the Gore box and with the agreement of the countries concerned, and we collected data from places like east of Greenland and just north of Greenland, where this very heavy ice was. Although they're outside the Gore box, that was acceptable to Denmark and Norway. Next slide, please. There's other ways of getting ice thickness now. You can go with an aircraft, with a laser that measures the thickness, and gives you an image in the same way as an upward-looking sonar, like the picture on the right. You can see how much ice there is on top, at the top, and you can then multiply it by some magic number to get the ice thickness at the bottom. Next slide. But now, for the last 10 years, I've been working mainly with unmanned vehicles, and that's a lot more work to get a small amount of data. These are called autonomous underwater vehicles, AUVs. They're like torpedoes. They're programmable to follow a fixed route under the ice and then come back to where they started out from. And they have the same sort of multi-beam sonar as a submarine does. So in this particular case, this is a small AUV, and we were using it under this ridge on the right-hand side, operating it from the tent at the back of the picture. Next slide. And one of the disadvantages is you have to build your own camp, which you don't have to do with the submarine. So can you do the next 2 slides together? Yeah, just see, that's building your camp. And the next one, you have to leave a hole in the floor to put the AUV through it. This is north of Ellesmere Island. Next slide. And this is the kind of data you get. It's very, very good quality because you can run the vehicle very close to the ice because you don't have to worry about people being inside and danger to them. So you can see this very, very high quality image of a pressure ridge upside down. And the circle shows a region where you've got a lot of ice blocks pushed down, and we sent a diver down who showed that is actually what you see in reality. Next slide, please. And this is a more typical view without a ridge, but with a lot of deformed ice points and a lot of flat ice. So this is the sort of landscape that will be generated for you by an AUV, but it's much slower than a submarine. You can't get a 1,000 miles out in a couple of days. Next slide, please. And this was the first results that came out of this were very important, because it was the first evidence that sea ice is getting thinner. I did this paper in 1990. On the left, you've got contours of mean ice thickness from the area between Greenland and the North Pole in 1976, and we see 5, 6, and 7 meters as you move towards Greenland. The right-hand one is the same set of tracks that the submarine followed in 1987, and you only have 4 to 5 meters. And then the circle is the submarine not doing that grid, but just going past the north of Greenland and only finding 2 to 3 meters of ice. So a huge loss of ice. And we found that loss was equivalent, even in 1987, to 15%. Oh, it works again. So in the meantime, the Americans have been collecting data from other parts of the Arctic and were finding similar losses. We got 15% in 87, and then when we worked again with later data, we were getting more like 40% loss of thickness, and the Americans were also getting 40%. So we agreed on our loss of ice from every part of the Arctic was about 40% of thickness. It's now more like 50%. Oh, this works. Well, okay. Now, if you take the thickness and the area together and look at that gives you the volume of ice. And when we look at the summer volume in September, we find that back in the 1970s, we were getting about 16,000 cubic kilometers of ice, but now we're down to 4,000. So there's only about a quarter as much ice in terms of volume in the Arctic in summer as there was back in the late 1970s. And this has been represented by a thing called the Arctic death spiral. I didn't think that name up. That was somebody in Colorado. But what you look at here is the volume of ice in each month of each year. And you start off at 12 o'clock on the clock, and you look at how the ice volume changes from year to year as you go round towards the present day. Now, if there were no change going on, you'd have a set of concentric circles for different months of the year. But as it is, we can see that the summer months are zeroing in towards the centre very fast. So September, August, and October are getting close in towards zero, while even the winter months are losing ice volume, and that's quite a serious change. Okay, the August change is something that is showing, for extent, it's showing a linear decay still, taking us down towards zero, but of course the thinning means that it is actually declining relatively faster than this. Right, next slide, please. Now, one of the results, so let's look at the impacts now. One of the results of this is that there's a large amount of open water in the Arctic in summer. This shows in August of 2015, we can see that the red and the yellow is ice, the blue, of course, is sea, and this is the Beaufort Sea north of Alaska and Siberia. And with this amount of open water, there's the possibility of generating quite large waves. If you have a storm, you can get waves which are as high as you're getting in any other ocean, and those impact on the ice and break it up and cause it to retreat faster. So that's a first feedback, which is a feedback mechanism tending to make the ice retreat faster. And we measured this in a big program with the Office of Naval Research back in 2014-2015, and it involved putting out 30 wave buoys and a lot of associated instrumentation over a huge line from the edge of the ice in towards the center of the Arctic. So I mention this because it was the first effort to see what the effect of waves is on ice as the ice retreats. But also, we had an enormous help here from COPRI, the Korean Polar Research Institute, because they used their icebreaker to take out these buoys, and we used their helicopters to install them. So all of those buoys were put in with the help of Korea. And then we did later experiments where we just used individual wave buoys, looking at effects like what happens when the ice is trying to advance but can't advance because there's too much wave action there. It breaks the ice up into small lumps called pancake ice, and that melts again quickly and means that the ice doesn't advance as fast as it should do. So we've been finding that not only do the waves break the ice up in summer, but they prevent the ice from advancing in the autumn. So they do have quite a big effect on the ice extent. Then the other things we notice about the changes that are going on are that, for instance, you can't do experiments in the Arctic Ocean anymore involving building camps on the ice. This is what we used to do in 2007. You have a camp with about a dozen wooden huts for the scientists, a mess hut, a generator hut, a scientific hut. All this has to be installed by helicopter or aircraft. Mainly this was done by aircraft, and then maintained for about 2 months, and then taken out again. Now that can't be done if the aircraft can't operate, and you could always rely in the past on the ice being stable during the winter and being thick enough to have ice runways, so you just fly your aircraft in and use the ice as a runway. But now you can't do that anymore because the ice is breaking up and is much thinner. So when we do experiments now, we have to freeze a ship into the ice and then get back on board the ship if the ice breaks up. And it's also dangerous, of course, for indigenous people. This is an Inuit hunting group in northwest Greenland, hunting polar bear. And here we help them by putting a radar on the bottoms of their sledges to tell them how thick the ice is, because there have been cases, increasing number of cases, where they've gone through the ice, even in the winter. So this is what happens now in winter in the Arctic. Instead of it being a very stable area, it's now typically breaks up very frequently because it's much thinner. So when you have a storm, the ice breaks up, and we can see now, this is right across the Arctic from Alaska to the Canadian Arctic, and the blue here are leads where the ice has broken up. And you can see you couldn't really operate a runway for an aircraft very safely in this kind of conditions. The advantages the Arctic offers when it's in this state, unfortunately, it makes oil drilling easier, because a typical drilling technique now is to use a floating drilling platform. That's the circular platform, which is anchored to the seabed, and it has to be, the ice around it has to be broken up all the time to stop the ice forces from being enough to drive it off station. So you have an icebreaker circling around the drilling rig, and if you don't have much ice, or if you don't have any ice, this process becomes much easier. So this is a nostalgic view of what the ice used to be like. This is multi-year ice, and it's really rugged stuff. This is what people who tried to walk across the Arctic had to contend with. But today, this is what it looks like from underneath. But today we don't get that anymore. Oh no. Okay, we don't get that anymore. Just to show, again, the changes that happened, this was the first time I went to the Arctic in 1970, and we were trying to get through the Northwest Passage in a Canadian ship. And the ice was broken up. This was very heavy, thick ice, multi-year ice, that you couldn't break through. You could just try and push through it. And then this was 1970. This is 2014 in exactly the same area of the Arctic, in fact, further north. And you can see how pathetically thin the ice is. You can't really safely even walk on that ice. And within a week, it melted. This is exactly the same time of year as the previous picture, and it shows the difference between 1970 and 2014. So we can see how that's happened because we have sensors, satellite sensors can distinguish between first-year and multi-year ice. And multi-year ice used to be dominant in the Arctic. That's the red colour. And as recently as 2004, it was still dominant, and then it rapidly retreated partly because of thinning, because of warming, and partly because of changes in the currents. And now there's scarcely any multi-year ice left. And this is what we get. This is my background picture, which is modern first-year ice in the Arctic. Very, very thin and not very exciting. So now look at what that does to the climate, and I'm afraid I'm overrunning a bit. The first thing is that the retreat of sea ice causes an albedo change to the planet, which means that warming is accelerated. Also, we get an accelerated melt from the Greenland ice sheet, which leads to an increased rate of sea level rise globally. There's also a threat, which I'll talk about, from Arctic methane, that may produce a very large pulse of methane that could cause a sudden significant change in global air temperatures. And there's an extreme weather effect, which we're suffering from already this year. And there's a decline in strength of the global thermohaline circulation. So I better talk about these quickly because I'm behind. So the albedo change is that this area that's shown in blue is area that used to be ice-covered in summer and isn't now. And that has an albedo which is about 10% or less. That is, the amount of shortwave radiation from the sun that's reflected straight into space is about 10%, whereas when it's fresh snow or ice, it's more like 80%. So when sea ice melts, you're suddenly replacing a surface with 80% albedo with a surface with 10%, and the result is a very large increase in the amount of radiation absorbed by the surface. This estimate that was done in that previous picture was that it's equivalent to adding about 25% to the direct warming due to adding CO2 to the atmosphere. So you're getting an extra quarter to whatever you do. But I think it's worse than that. I think it's more like 50%. And the reason is, I'll speed up here, is snow, because the snow line has also been retreating in the Arctic. And the brown here is areas that used to be covered with snow in June. And of course, these are areas you always think of as covered in snow. That's Alaska, the Canadian Arctic, Siberia, good snowy areas. But they're not covered in snow anymore in that time of year. The snow is melting earlier. And so just when there's the maximum solar radiation, you're replacing again snow-covered surface by ordinary land, which has an albedo of less than 10%. So the anomaly there relative to the 1970s is about 6 million square kilometers. So that's 6 million square kilometers of the northern hemisphere that used to be snow-covered in summer is now not, or early summer is not snow-covered anymore. And that anomaly is as great as the sea ice anomaly. So really and truly, if we add the snow and the sea ice together, then the impact is more like adding 50% to the amount of warming that you would simply get from adding the carbon dioxide alone. So this feedback is increasing global warming by 50%, which is quite a big amplification. The second effect is as the sea ice retreats, warm air wafts over the Greenland ice sheet in summer. And the Greenland ice sheet is an elevation of about 2 kilometers, so it's very cold, and in the past it never melted at all, even in summer. And then in later years, it started to melt around the edges. That's the left-hand picture here, where there's low elevation. And then in the most recent years, it started to melt all over. So you have the entire surface of the Greenland ice sheet is suffering from melt in summer, but the meltwater runs down inside the ice sheet. Previous glaciologists thought there's nothing much to worry about because it freezes again in the winter. But it doesn't stay in place. It goes down holes in the ice sheet called moulins, which take the water down through the ice sheet and spew it out near the bedrock, where it pushes out glaciers and causes an increase in the flow of glaciers and in the amount of icebergs going into the ocean. So this big increase in the amount of fresh water going into the ocean from Greenland is something we can measure now using this gravity satellite, the GRACE mission, and we can see the loss of ice is accelerating. Oh no. Can you show the next slide, please? Oh, here we are. And this is causing an increase in, okay. I think it didn't show the last one. Well, this is, no, can you go back about 3 slides? Okay, that's it, yeah. The predictions of what global sea level will be like by 2100 have been, were quite complacent in a way, but Intergovernmental Panel on Climate Change didn't take account of the melt of the Greenland ice sheet initially, so they were only predicting 20 or 30 centimetres. And then the more you took account of the melt and of the extra processes of melt which are going on now, the higher the rate of warming got. So now most predictions are that there will be at least 1 metre, and some scientists like James Hansen are predicting there'll be 4 metres. And it's important to get this right because the impact on global policymakers is enormous. You've got to know how much you have to raise the heights of sea defences around the entire coastline of your country. And so it's important that we should know this figure. The trouble is it keeps increasing as we measure more effects going on with the Greenland and Antarctic ice sheets. And the other thing about it is that you're tempted to think that a fairly small increase in mean sea level, say 1 metre, it's bad, but you can imagine building seawalls 1 metre higher around an advanced country that can afford it, not Bangladesh, for instance. But a raise in mean sea level gives you a very big increase in the probability of a disastrous event. So here the middle curve shows the distribution of sea level heights in a normal world with tides and wind and so on, with the little black area being the probability that it exceeds the mean enough to give you a disaster. Then you shift the mean by a fairly small amount to the dotted line, and the probability of the disaster is now the cross-hatched area, which is much greater. So you imagine that a change in sea level gives you a moderate effect on phenomena, but it doesn't. The probability of a disastrous flood is greatly increased if the sea level is raised, and the probability goes up much faster than the rate at which you raise sea level. So this means much more frequent floods, for instance, in the Bay of Bengal. Then the methane threat, I'll talk about it very quickly, is that the problem with the Arctic Ocean is that it's it's two-phase ocean. Most of it's about 4,000 meters deep, that's the dark blue, but it has very wide continental shelves, which is the light blue, which are only 50 to 100 meters deep. So these are really shallow little lakes, and then there's a very deep part in the middle. But the trouble is, as we see sea ice retreating in the summer, it's retreating from the edges into the middle. So the part that's left, the part that's still sea ice covered in summer, is the central Arctic Ocean, which is deep water, while the part that's around the edges is exposed. And because it's exposed, it absorbs more solar radiation, and because it's shallow, that radiation reaches the bottom and warms the seabed. And we find, for instance, in this left-hand map, seabed temperatures of 3, 4, and 5 degrees being measured in summer. And we measured temperatures of 11 degrees in a recent year. And that warming of the seabed melts permafrost. The coastal seas north of Alaska, East Siberian Sea, and the Kara and Laptev seas have got a layer of permafrost left over from the last ice age, and that's holding down a mass of methane. And if that permafrost thaws, that methane will be released, and it's already being released in places where it's been studied. And the methane, when it's still in the sediments, is in the form of methane hydrates. That's this stuff which looks like ice. And in fact, it is ice, it's mostly ice, but methane molecules are contained within the structure of it, and it burns. And so if you put a match near that, it will catch fire. And this stuff comes out the seabed, it disintegrates, turns back into methane, and comes up in these big plumes. And this is 60 meters water depth in the East Siberian Sea. We're looking sideways at a series of plumes rising from the seabed, carrying methane up to the surface. And here we see, with a underwater vehicle going through that, you can see the actual methane bubbles rising to the surface and flattening themselves against some ice on the top. Now, this methane dissolves in water, given time, but it doesn't dissolve in 50 meters of water. It comes out too quickly. So this methane is getting into the atmosphere. And for a while in recent years, it was thought that we got the methane problem kind of licked by the Russians being more careful with their pipelines and other sources of methane, with which there are many, being kept in hand. And the level reached some sort of fixed point, of about 1770, and it stayed that way for a decade. And we thought, well, people thought methane was not going to keep increasing the way that carbon dioxide does. But then in the last few years, various methane monitoring stations showed it increasing again. And the most serious one is this monitoring station in the Arctic at Alert, where the red shows the last few years, and it's increasing fast. And on top of that, there's these little green blobs that you see at the top, which are not erroneous measurements. They're little pulses of methane coming out and reaching the recorder. And that's been called dragon's breath by the scientist who investigated them, because he thinks that that's these pulses of methane coming out, blowing across, reaching the recorder before they disperse. And so it literally is like dragon's breath, because it's inflammable. And and you can measure this from satellites as well. The right-hand side shows methane concentrations 3 years after the left-hand side, and they've gone up significantly in the Arctic. These are measurements done looking down on the North Pole. Sorry, I'm sorry, I might have to overrun by a couple of minutes because I had to stop in the middle. Okay, so we see that the big methane increase is in the Arctic, and so that's giving us evidence that it's the Arctic that's the source of continuing increase in methane levels. And the fear is that a huge amount of methane could be released in a single pulse if all of this seabed permafrost melts and releases the methane. So we did a study of what that would do to the climate, and here the blue is the expected warming of the ocean, warming of the planet in the next few decades. The red is what we get if we had a 50 gigaton release of methane, and it would give us a 0.6 of a degree of warming very suddenly, and that would be pretty catastrophic, I think. And this sort of thing may have happened in the past, because when methane is released, you lose track of it. It gets oxidized in 10 years, and then you could have an event that doesn't leave any trace in the geological record. Now, permafrost is warming up. The things I wanted to get in were something that is happening to us now, which is that extreme weather events. And this can be related to Arctic sea ice, or at least to Arctic temperatures, according to the generally accepted theory now of Jennifer Francis, is that it's a product of the changes in the jet stream. The jet stream is the very strong wind that separates Arctic air, that's at the top here, from more tropical air at a lower latitude. And the jet stream is usually, or used to be, fairly straight, blowing you eastwards if you're flying eastwards in an airliner. But now it's slowed down because the Arctic has warmed up faster than the rest of the world. The temperature difference between the two air masses has gone down, and that's slowed down the driving forces for the jet stream. So instead of going in a straight line, it goes in lobes like this. And these lobes move very slowly, and you can see that what they do is force polar air down to lower latitudes than it ought to reach. Like here, polar air is reaching the eastern United States, and tropical air up to latitudes also that it shouldn't reach. So here tropical air is reaching the Canadian prairies. And this happens all around the world, but we noticed it, meaning it was noticed in Europe early this year when we had a very cold spell with very warm air temperatures in the Arctic, 30 degrees warmer than normal. And here in Korea as well, you've had very cold weather during the winter and very hot weather in the summer. And this depends on where you are in relation to these lobes. Now, the trouble with these lobes is that they're occurring in mid-latitudes. The anomaly is occurring at 40, 50 degrees north, and that happens to be the latitudes where most of the world's crops are grown. That's the brown is the chief crop growing area. So if you have unusually hot or cold weather, you're going to affect crop production very seriously indeed. And this can be seen from this graph, which was the World Food Price Index that was developed by FAO in the year 2000. It was 100, I think, and it started to rise. And in 2008, it reached 220. And then it went down again, and it went to a higher peak. Those peaks corresponded to times of exceptional retreat of Arctic sea ice. And you can see that the person who drew this curve has correlated these peaks with social unrest, because when you're living in a third world city and you can't grow your own food and you're poor, the price of food really matters. And so that the Arab Spring, for instance, was related in many ways to this 2008 peak. So we can see that not only would extreme weather events lead to overall loss of crop, loss of food production, but would hit particular areas hardest, and that could cause a lot of social unrest or warfare even. And this looks worst of all if we consider the projected population figures for the end of this century. And This is a UN World Population Prospects, and it does this by region, and it's looking at the year 2100. I'm afraid this picture's got slightly shoved over, but it compares 2100 with 2015, and we can see most parts of the world have increased in numbers. Europe slightly decreased, but the most extreme case is Africa, which is pretty much going to quadruple in numbers of people by the end of the century. Now, it's very difficult to see how that's going to be possible to feed that number of people. So on top of this natural population increase, which is producing a major impact on the African continent in particular, we have the fact that the growing, food growing is going to not be as straightforward as it used to be. The Green Revolution can't occur if you haven't got any possibility of predicting whether you're going to have growing conditions that are good or bad. And we know that if the temperature rises very much, then there'll be a loss of yield of most crops. And one of the reasons why 2 degrees was chosen by as the limit by the Intergovernmental Panel on Climate Change was, by the UNFCCC as the maximum we could tolerate, was that beyond 2 degrees of warming, there's losses of yield of nearly all crops, and so that's nasty. But loss of warming plus unpredictability is even worse. So I'll leave this out. Unfortunately, I'm running out of time, but I'll just try to finish on what we can do. And what we find is that we're not reducing our carbon emissions at the rate in which we should do. The Paris Agreement was a tremendous step forward because for the first time every country in the world agreed to reduce carbon emissions according to a plan which could be tightened up as time progressed. And that gives us a way forward, perhaps. But firstly, not all countries are doing it. China and India are not. Even Europe and the USA, they're only reducing their emissions a bit because we transferred so much in industrial capacity to China and India. So the overall CO2 levels in the atmosphere are still rising exponentially, and the hope that you can hold that back is, I think, a vain one. So we have to go to other ways of getting warming down, and the Intergovernmental Panel has more or less admitted that by saying that all the scenarios that will give us 2 degrees of warming involve taking carbon out of the atmosphere. And we can do that we can do one of two things, or both of two things. One is adopt some amazing technique. I like this one because it was developed by some colleagues in Edinburgh University, which is called marine cloud brightening, where you pump up seawater through fine nozzles into the bases of marine stratocumulus clouds, and it makes the clouds brighter, and they increases their albedo, they reflect more radiation. So that's a way forward there, and that's called geoengineering, but it doesn't do anything about the carbon dioxide content of the atmosphere, and in the long run that will really do you in, because the carbon dioxide causes acidification of the oceans, which will end up in removing marine life. So this is a sticking plaster solution that can hold back global warming if we can't manage to hold it back by reducing carbon emissions. But in the end, we have to take carbon out of the atmosphere, and this is just what we do to the oceans. We have to take it out of the atmosphere, and there's various methods have been developed that work, and pilot plants have been set up to absorb carbon dioxide onto chemicals and then reconstitute the chemicals. And there's a plant in Iceland and a plant in Canada and one in the US. But in the end, those need to be much more heavily funded. It needs to be a global effort, because if it's CO2 that's causing global warming, then the cure for global warming has to be removing CO2. It's as simple as that. And if we can't do it by benign methods, we have to do it by some technical method, and that means looking at these engineering techniques and developing them so they become cheap enough to be used. And that's my plea really for the world, is even if you don't like technical solutions because you don't think they'll work, we have to use that if we're going to get rid of or get climate change under control, because I don't think anything else will do it. Okay, thanks. Sorry to have overrun, but
Peter Wafts, would you please get back to your seat for a while? Yes. 소중한 강연을 해주신 우리 피터 와담스 교수님 다시 한번 감사드립니다. 이 시간은 간단하게 저희가 출판 기념식을 준비를 했는데요. 앞서 말씀드린 바와 같이 와담스 교수님께서 제기하신 기후변화에 관한 깊은 통찰을 공유하고자 경희대학교 출판문화원에서 와담스 교수님의 대표 서적이신 Farewell to Ice를 한글로 번역 출판했습니다. 제목은 빙하여 자리거라입니다. 이 서적을 지금 총장님께서 직접 와담스 교수님께 전달드리는 시간을 갖도록 하겠습니다. 우리 총장님과 와담스 교수님을 다시 한번 앞으로 모시겠습니다. 여러분 박수로 맞이해 주시기 바랍니다.
University for volunteering out of the blue to translate this book and publish it, and so that it can be read by Korean readers. And I'm very grateful for that, and I hope that it does well and that people get the message. But thank you, President, and thank you for taking this book on.
Thank you very much. 대단히 감사합니다. 여러분 큰 박수로 다시 한번 축하해 주시기 바랍니다.